Let's try out our new formula to compute a couple of directional derivatives. So suppose we want to find the rate of change of the function f, which is going to be a polynomial given by x squared y cubed minus 4y. And we want to look at how it's changing at the location 2 minus 1. And we want to look in the direction or parallel to some vector v given by 2i plus 5j. Okay, so that's physics notation. More often I would write this as like 2, 5, but whatever. So let's see. So the formula that we saw in the last clip was that the derivative, the directional derivative, is given by the dot product of the gradient at that location and the vector u that you're looking at, right? So those are the ingredients that we're going to need. So we'll go ahead and compute the gradient of the function that's been given to us. And it's a polynomial, so that's not too tricky. We get 2xy cubed for the first coordinate. The x derivative of the 4y term, of course, is just 0. And then when we differentiate this guy with respect to y, we get 3x squared y squared minus 4. Then we're also going to need our direction. And a direction is a unit vector. Has to have length 1 or it'll mess up the computations. So we're going to need u to be a unit vector, which means we take the direction we're given and we divide it by its length in order to get a unit vector. And so if we compute the length of v, let's see, so we've got 2 squared plus 5 squared square rooted in the denominator. So that's 1 over root 29 is going to be our scalar multiple of v. So v looks like 2 over root 29 in the first coordinate and 5 over root 29 in the second coordinate. All right, so that's our unit vector u. All right, and then I guess we need to evaluate the gradient of f at a. So the derivative in this direction of f of a is going to be grad f evaluated at a dotted with u that we just computed, which is going to be, so now we evaluate this at the location a, and we find that it's minus 4, 8. And then we take the dot product of this with 2 over root 29, 5 over root 29. And we get, let's see, so there's a common factor of 1 over root 29, which I'll stick out in front because it annoys me. And then we have minus 4 times 2 plus 8 times 5, computing the dot product. And collecting the terms inside the parentheses, I get 32. So that's how quickly f is changing at this location if we move in that direction. Yeah, so it's when we say in the direction is a unit vector, that means how fast is f changing when we move in that direction at unit speed, right? Because if you go along that parameterized line really fast, then you say, oh, f is changing really fast, but no, that's just sort of a confounding thing. Let's look at another example. Let's go back to this example that we saw before. X e to the y at the point 2, 0. And so when we looked at this example before, we found that the gradient of f at this location was 1, 2. Okay, so and then I asked you how fast is f changing if we move from A to the location B given by 1/2 2. And I told you we'd need directional derivatives to work that out. Gradients just don't cut it. Okay, so let's see. Well, we're going to need the vector from A to B, and that's given by just B minus A. And so that's minus 3 over 2, 2. And so let's see this, but that's not good enough for what we need here because we need a unit vector. So for a unit vector, we'll have to divide by its length. So the length of this displacement vector is going to be 9 over 4, and then 2 squared is 4. To put it over a common denominator, I guess that's 16 over 4. Then we'll have to take the square root of the whole thing. And on top we've got 25, which has a square root of 5. And on the bottom we've got 4, which has a square root of 2. So the length of this displacement vector is 5/2. So that tells us that we should take as our unit vector u equal to AB over magnitude of AB, which is, let's see, so we've got minus 3/2 divided by 5/2 is times 2/5, and then 2 divided by 5/2 is 2 times 2/5. And simplifying that a little bit, we see that u is minus 3/5, 4/5. Okay, so that's our unit vector. So then the directional derivative of f at A in direction u is going to be the gradient evaluated at this location dotted against the unit vector pointing in the direction that we want. And so our gradient at this location is 1, 2 from prior calculation, and that's dotted with minus 3/5, 4/5. And so working out the dot product, we have minus 3/5 plus 2 times 4/5, and that gives us so 8 minus 3 is 5, so we have 1. So the rate of change is 1. So for if we're moving at unit speed in that direction, the function is changing at unit speed as well.